Hi, and welcome to Group 25's presentation on complex systems. A complex system is a network of components that act and react to each other. Components can be humans, organisations, organisms, planets, and many other things. Complex systems can be found all around us and even within us. And so complex systems apply to many different scientific fields. This often means that definitions of complex systems can vary. Generally though, in a complex system, the actions of individual components make up the behaviour of the whole system, and no component has complete control of the system. Rather, the system has dispersed control amongst all the components. An example of a complex system in the world around us is the economy. The economy is made up of many different components. You have businesses supplying goods and services, consumers deciding where and what to buy, investors choosing where to invest their money, resources used in production, and the government collecting taxes and providing services. Each one of these components acts and reacts to the other components, but there is no one component that controls the system. The economy becomes extremely complex as each component's actions are affected by its values, education, technology, and its political system, which themselves can be thought of as components. The result of this complexity is a lack of understanding and an inability to predict the future of the economy. And in the case of the economy, its complexity can lead to unforeseen chain reactions, leading to catastrophic results.
Not every complex system is created by human beings. In fact, the nature is the greatest creator of complex systems. Have you ever observed thousands of birds flocking into the sunset? Did you ever wonder how they form and maintain their flying pattern without bumping into each other? This is the magic of a complex system. Surprisingly, there's no leading bird or central control in the group, and each bird only follows certain rules that enable them to perform this dramatic piece of art. Since complex systems have more components, they are more difficult to maintain and troubleshoot. Sometimes, things do go wrong. On the 1st of July 2002, a Russian passenger jet Tu-154 bound for Spain received a collision warning from onboard TCAS, or Traffic Collision Avoidance System, that tells the pilot to climb immediately to avoid the incoming traffic. Meanwhile, the Tu-154 crew received another command from ATC, or the air traffic control, to descend for the incoming traffic. The crew only had 8 seconds to decide which command to follow. Since the command from ATC was given high priority, the Russian crew decided to descend as instructed by the ATC, not knowing that there was another DHL-757 cargo plane flying right below them. 8 seconds after TCAS warning, the Russian jet flew into the DHL cargo jet, killing 69 people on board.
So what are some of the key characteristics of these complex systems? There are 4 key characteristics of any complex system: emergence, non-linearity, self-organization, and an edge of chaos. Let's now have a look at these in some more detail. Emergence is the overall result or creation of an entity that is formed by the relationship between components. Components may not show signs of being able to form this entity if considered on an individual basis. This can be pictured through the formation of a snowflake, where raindrops combined to produce this overall entity. Complex systems do not show linear behavior, meaning that the small workings of a component can have a great effect. Picture the butterfly effect. As a result, the systems can go from a stable state to a non-stable state without warning. There is no central control in a complex system, nor is there a hierarchy. Instead, components are integrated to form a functioning system. There is interconnectivity between the components, meaning the actions of one can affect all the others. The relationship between the components is considered more important than the components themselves. Components tend to find their place naturally, but this is not always the case. All complex systems exhibit an edge of chaos. This is often referred to as the tipping point of the system and is the point of maximum productivity. This is the state just before the system begins to break down and where a chaotic state is about to be reached. At this point, the system ceases to function and is in danger of imploding.
What is adaptive complex system? They are special case of complex system. They are complex in that they are diverse and made up of multiple interconnected elements, and adaptive in that they have the capacity to change and learn from experience. For example, the stock market, the ecosystem, and our brain. Feedback and co-evolution are essential to the working and survival of all regulatory mechanisms found throughout living and non-living nature, and in man-made systems such as education system and economy. For example, the evolution of a plant will affect the evolution of the animal that eats the plant, which in turn affects the evolution of the plant, affecting the evolution of the animal. It can adapt and evolve with the changing environment.
And then is the complex system relevance to engineering. There are three parts include engineering complex system, comparing traditional and complex system engineering, and engineering system failure. Many examples of complex systems that derive from engineering that have greatly impacted our lives, such as electrification, the internet, and highways. In engineering complex system, engineering is not about letting systems be, it's about making things happen, about convergence, optimum design, and consistency of operation. Traditional system engineering is appropriate for managing the decision-making processes of individual autonomous agents in a complex system. Complex system engineering must be added when multiple autonomous agents are part of any solution, or when multi-scale analysis becomes essential to a significantly complete characterization of an evolving problem and its solution. Complex system engineering changes the focus from here is the solution designed from the requirements, now go implemented, to here are the selective pressures acting on the elements present, now resolve or reduce them. The term product is used to identify the outcome of traditional system engineering, and the term enterprise is used to identify the outcome of complex system engineering. And here is the example of engineering complex system failure. The sinking of Titanic is perhaps the most well-known complex system failure in history. The disaster was caused by compound effects of structure issues, management decisions, and operating mistakes that led to the Titanic loss of 1,495 lives.
We, as human beings, are a part of the planet's complex system. The direction of which we take it could be disastrous if our understanding is not paramount.